Once again, I remind you, my name is Professor Duke Orata. This is our 5th lecture, and today we are going to look at things to do with internal energy and bomb calorimeter, which are very useful equipment for determining the energy content of substances. So let's once again just assume, as we had already said in earlier lectures, that U, which is internal energy, is a function of volume and temperature. And like we have said, U, internal energy, is a thermodynamic state function. In other words, it depends on the initial and final states of the system, not on the path of the process. And this can be illustrated just diagrammatically by having a situation where we have, for example, if this path was adiabatic, let us say, where heat is allowed to the system, and this is a non-adiabatic path, then if U was not a state function, then you'd have expected that if we started at, say, point 1, then we'd end up with point 2, where U2 is not equal to U1, which would mean that if U2 is not equal to U1, then we have generated some energy, and that would violate most of the laws of physics, because we cannot have a perpetual motion machine. Therefore, U definitely is a state function. It depends only on the initial states and the final states of the system. So, what does that mean? We say that a thermodynamic state function is an exact differential. And we say that if it's an exact differential, then you can write the total derivative of this internal energy, du, as del U, del V, dV, T constant, plus del U, del T, V constant, dt. Because it's an exact differential. And we have said all state functions are exact differentials. Remember, we talked of heat and work in earlier lectures, where we said heat and work are path functions. They depend on the path you follow. That's why if you have a adiabatic process, Q is 0. Non-adiabatic process, Q is not equal to 0. And so if we look at this particular expression here, first of all, we want to relate this state function to a thermochemical observable. Work and heat are thermochemical observable. So we are saying that U is a state function, and Q, W are thermochemical observables. Thermochemical observables. And the relationship between state functions and thermochemical observables is very critical. It's very, very critical in applications of thermodynamics. Let us see how we can relate U and enthalpy H as state functions in relation to thermochemical observables Q or W. So, for example, if we remember that CV, which was the isochoric heat capacity, we had said was del U by del T, V constant. We said that CV was del U, del T, V constant. And also we saw from first law that du was dq plus dw. But we have also mentioned that in general PV work, dw, PV work, dw, very important to remember that, is minus P dV. Always remember that. Therefore, PV work, dw is minus P dV. So in place of this dw here, we can put in P dV, so that we are saying that du therefore is equals to dq minus P dV. So under constant volume, if you constrain the system to constant volume, if the volume is constant, then you know that this dV will be 0. In other words, there's no change in volume, so that this quantity will be 0. So du will be equals to dq, and now we can put a subscript v there to indicate that it is heat transferred on a constant volume. So the change in internal energy, or the internal energy, can be determined if you do those measurements under constant volume. You just do the heat measurements under constant volume, or heat transferred under constant volume will give is equivalent to the change in internal energy of that system. And we are going to see this in bomb calorimetry. And the most important thing to note here again is that U is a thermodynamic state function. It's a state function. And Q is a thermochemical observable. So in this expression here, we are relating a thermodynamic state function to a thermochemical observable. And this is the basis of thermochemistry. That is the basis of thermochemistry. Thermochemistry is based on that relationship there. The relationship between a thermodynamic state function and a thermochemical observable. Let us look at the other very important thermodynamic state function which can be related to a thermochemical observable, and that is enthalpy. Enthalpy, H, which normally is a function of temperature and pressure. H is enthalpy. And enthalpy, in general, H is equals to U plus PV, where U is the internal energy, just like we have already talked about, P is the pressure of the system, and V is the volume. Notice that when you're talking of H is equals to U plus PV, don't always assume that this PV is nRT. That is only true if you are dealing with an ideal gas. If you are dealing with an ideal gas, then in that particular case, H can be U plus nRT. Otherwise, it is just the pressure and volume of the system. So, if we allow this quantity to change, let us say the enthalpy changes by some infinitesimal amount dH, U changes also by some infinitesimal amount du, P by some infinitesimal amount dP, and V by some infinitesimal amount dV. That can be gotten simply from using product rule. We can just use product rule. For example, if you take the derivative of xy, let's call it uv for ease of reference, uv, then that becomes u dv plus v du. That's product rule. This product rules in calculus. That's product rule. Product rule in calculus. So if we apply that product rule to that enthalpy expression, then we have dH will be equal to du plus P dV plus V dP. Very important for us to note that. Now, we know that du from first law of thermodynamics, du from first law of thermodynamics, we said was dq plus dw. That is, du from first law of thermodynamics was dq plus dw. So we can put that dq plus dw there, and remember further that dw, we said work, PV work is minus P dV. So we have that expression. So dH can now be written as dq minus P dV plus P dV plus V dP. Remember, this quantity here is du from first law of thermodynamics. Law of thermodynamics, which we did the other time. So that's from first law of thermodynamics. So obviously those terms will cancel out. So we have dH is equal to dq plus V dP. And under constant pressure, why have we chosen constant pressure? Remember that Cp, that's the isotonic heat capacity, as the expression for enthalpy, that's del H, del T, pressure constant. So under constant pressure, dP will be 0, so that we have, so under constant pressure, keep pressure constant pressure, P, we will have dH is equals to dq P. So what does that mean? It means that the change in enthalpy can be determined when you do measurements of heat transferred in that process under constant pressure. Again, that is a thermochemical. That's a thermochemical observable. That's dQP, and this is a thermodynamic state function. Thermodynamic state function. So once again, you are able to relate a thermochemical observable to a thermodynamic state function. And this is the basis of thermochemistry. Thermochemistry is very important in thermodynamics and in measurement sciences. For example now, let us look at bomb calorimetry, where we use this observation. Let us look at bomb calorimeter. This measurement or this instrument is used to determine the energy content of substances. For example, if you want to know the energy content of a margarine or some peanut butter or some fuel, then you'll have to use bomb calorimeter so that you're able to compute from the experimental data which you get, or what you call empirical data, what the values are. And so if we go back once again to U, internal energy, as a function of temperature and pressure, and write it as an exact differential, then du, once again, is del U, del V, dV, T constant plus del U, del V, del T, dt, V constant. We already know that del U del T is the isochoric heat capacity. But we don't know what del U del V is in this particular case. Del U del V and a constant temperature. So the first thing we have to do is to figure out what is the value of this coefficient here. What is the value of this coefficient here? How do we determine it? So suppose we set up an experiment. We have an experiment, and that experiment we normally refer to as Joules experiment. Joules experiment, where you have two flasks. And you have a tap here. Let's call that a tap. And this flask is filled. Let's say it's filled at a pressure X1. And this one is evacuated, so there's no gas there, it's a vacuum. And let us say we have a water bath. We immerse this in a water bath. The two flasks are immersed in a water bath. And we have a thermometer here. So what is the thinking behind this? So we have a thermometer. So what is the thinking in terms of this experiment? Because we are looking at how internal energy will vary with volume and a constant temperature. So under this kind of conditions, what we are thinking is, if you have this flask which is filled at some pressure and you have an evacuated flask, so when you open this tap, there will be a volume change. The gas will expand into the evacuated flask, point number one. And you have the thermometer. So if there's any heat involved as a result of expansion of the gaseous activity resulting from expansion, then we expect to see the temperature change. Now, in the Joules experiment, when you do this empirically, there is no change in temperature. No temperature change. So what does that mean? It means that dt is equals to 0. There's no temperature change. And very important, when the gas expands from the filled flask to the evacuated flask, that is called free expansion. And there's no work done when there's free expansion because there is no opposing pressure. We said that dW is pressure external, dV. Remember, this expansion is an irreversible process. If you look at the earlier lectures, we talked about irreversible work and reversible work, where we said irreversible work, the difference between the two pressures is significant. But in reversible work, which we talk of thermodynamic reversibility, that infinitesimal modification of a variable reverses the direction of the process. In that particular case, you can't, if it's the piston, is quasi-static. You don't even see the movements. So in this particular case, this is an irreversible work. So that the dW, that expansion, is an irreversible work. Expansion is an irreversible work, so we talk of dW for irreversible work. And that is minus pressure external dV. And since the flask is evacuated, the external pressure is 0. So 0. So that one we have what's called free expansion. Free expansion. Very important to note. And that means that the work done is 0. dW is equals to 0. So if you go back to the first law, then du now is equals to dq plus dW. There was no temperature change, so we are assuming there's no heat transferred, and W is 0 because we are talking of free expansion. So du is equals to 0. And we had seen that du was Cv dt plus del u del v of t dv. And this now is 0. That now is 0 because du is 0. So du is simply Cv dt. Very important. Note that. Now, this expression is only true when you are dealing with an ideal gas. This is only true for ideal gases. Ideal gases. And there's limitation with that Joules experiment in the sense that water was used as a bath and water has a large heat capacity. We already talked in lecture 2 about heat capacities, where we said it tells you the change in temperature when you apply heat to that particular system. So water having a large heat capacity, even if it happened that the expansion process generated some heat, you would still not detect it because to change the temperature of water by unit amounts requires a lot of heat. So this expression is only true for ideal gases. So for ideal gases, you can use that expression to calculate the internal energy. This is in the infinitesimal notation, or you can have it as delta U if you integrate the systems is Cv delta T. Now, this is a very important expression which is the basis of bomb calorimeter, which is used to determine the internal energy of substances. Bomb calorimeter is used to determine the energies of substances. So in this bomb calorimeter, we have a constant volume bomb. So let's just draw it schematically, just sketch it. We have a constant volume bomb. And we have ignition terminals here. We have a sample holder. This is immersed in water. There's a thermometer. We have a thermometer here. So we have a thermometer. We have a constant volume bomb. That means its volume does not change. Even on heating, constant volume bomb. We have the sample holder where you put your sample, which you want to determine its internal energy. And of course, this is put in a second container so that you can have air here, for example. Right? And we have a stirrer to stir this water. Let me get this out. We have a stirrer to stir the water here. So we have a stirrer which is able to stir the water. Let's call that a stirrer. So basically, what we have for the bomb calorimeter is very simple. We have the bomb unit, and of course, this will be connected to a detonation unit. So we have the sample holder where we have the sample. We have the constant volume bomb, which you say the volume will not change, is resulting from heat. And we have the thermometer, which will measure. We will use to measure the temperature changes. We have water here. This jacket is a water jacket. And of course, we have air or vacuum in that section there. Now, when you put your sample here and you burn it, in this case, we measure the temperature versus time. So you first of all will stir your system until the system equilibrates. so that the temperature is constant. So that if we have this graph here, where we have temperature and we have time, time can be in minutes, can be in seconds, whatever units you want to use, which is convenient for you. You first of all keep measuring the temperature and make sure that the system is equilibrated completely, and that will be shown with the constancy of the temperature. You see the temperature is constant. So when you ignite your sample here, you put your sample here, you put your sample here. When you ignite it, it will burn. When it burns, the temperature will change. So that's the point, what we refer to as the firing point. So you have fired your sample, you burnt it. That's you have fired the sample, firing here, this particular point. You have ignited the sample to burn. That's basically combustion. Combustion is total oxidation of a substance. So you burn it, that particular point. Remember, there is oxygen in this compartment here. In certain cases, you will find actually that we have this connected to an oxygen cylinder so that you are able to fill that oxygen there. There is a valve through which you can fill that oxygen into your bomb, and of course you shut it off so that you don't want to ignite your cylinder. It's shut off completely. When you are filled it, you remove that oxygen supply unit, so that you only have oxygen in the bomb calorimeter. And so when you fire it, there's combustion of that particular substance. It burns, and temperature will change. And so there will be a temperature change. You will see the temperature rise, and then it will start dropping off. Now, from what we have seen, that where we have a relationship between a thermodynamic state function and a thermochemical observable, remember in this particular case, the thermochemical observable is the heat, and the thermodynamic state function which you are talking about is the internal energy of that substance. So you go back to the expression which you got from Joules' experiment, that du, delta U, is equal to CV dt. So once you know the heat capacity of the water, and you know the delta T, which you have gotten from the graph there, then you are able to calculate the internal energy of your substance. Delta T is gotten from the graph. And your CV is the heat capacity of water. So if your samples are fuel, which is petroleum product, for example, you burn that, you are able to know the energy content of that particular fuel. So this is now a very practical application of bomb calorimeter.